Hello, everyone, and welcome to today's webinar, Filter Fume Hoods, Expert Insight on Improving Your Lab's Green Initiative. I am Sabrina Lemus of Labroots, and I'll be your moderator for today's event. Today's educational web seminar is presented by Labroots and brought to you by Labconco. To learn more, please visit www.labconco.com. Let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located on the top right of the presentation window and follow the process to obtain your credits. I now present today's speakers, Kasey Fulmer, and the Production Specialist at Labconco Corporation, and Kenneth Crooks, the Director of GreenFumeHood Technology at Labconco Corporation. For a complete biography on our speakers, please visit the Biography tab at the top of your screen. Kasey and Kenneth, welcome. Our speakers will now begin their presentation.
Hello, everyone, and thank you for joining us for this presentation on filtered fume hoods and improving your lab's green initiatives, with efficiency continuing to be a point of importance in building design and operation. One aspect of lab space that is often addressed first is the fume hood, as it can have a large effect on the HVAC system. Let us first take a look at the different types of fume hoods that can be found in many lab spaces. The first that we'll look at are the ducted. Now, ducted fume hoods can come in one of two sort of configurations. That would be the remote blower or the built-in blower models. And what we're going to discuss first is going to be the ducted hoods. The first one that we're going to talk about, the first configuration we're going to talk about, is going to be the remote blower configuration. This is the most common type of installation. This puts the blower on the roof or somewhere outside of the building, away from the fume hood in a remote location. Hence the type of configuration that is titled here. This also allows it to be a little bit quieter than typical because, as I've said, it's far away from the hood. Another aspect to the remote blower is that it can be sized for duct length. This includes the total length of the duct, the 90-degree bends, or any other sort of differences in your mechanical system. The benefit here is that no matter what you have, this can be properly sized for a blower that's going to work for your individual fume hood setup. They are also very safe. Remote blower puts the entire duct run under negative pressure, and that means that if there are any leaks or seams in the duct run, all the air on the outside of the duct is just going to be sucked into the duct and then exhausted through the building. So you're not at risk of any contaminants getting into a lab space with a remote blower having a duct system under negative pressure. Next, you can also challenge the blower with a damper. This typically goes between the fume hood and the blower, and that allows the system to be able to be balanced easier and ensure that the blower is operating within its most optimal range. This is a setup of a typical setup of a remote blower. You can see the zero pressure weather cap that's on the top. That does two things. It allows you to reach important height requirements of discharge for building codes, as well as prevents moisture or precipitation from getting into the blower and causing problems in that sense. So that's just what they typically look like. I wanted to make sure I showed that picture because it's pretty beneficial to see this setup. So next we're going to talk about the built-in blower configuration. These are for simple, economical situations, and they're ideal for short, straight duct runs in low toxicity applications. This is because it puts the blower right on top of the fume hood instead of on top of the building where there's a lot of bends and connections that need to be made between the two. They are generally noisier than remote blower installations. As I've said, this is a situation where it puts the blower right at the outlet of the fume hood instead of really far away with a remote blower. That means you hear the blower a lot better in this type of situation. The major downfall of a built-in blower configuration is the ductwork is under positive pressure. So in contrast to the remote blower situation, if there's a leak or in a seam or a crack in the ductwork, the components, the hazardous material that is being dealt with in the fume hood is actually going to be pushed out of those seams and into the lab space. So that's why all of this is for very simple situations and setups, because it's not the safest situation. And straight duct runs are a great way to eliminate that type of risk. So here are the associated costs with ducted fume hoods, and it mainly comes in the form of the mechanical systems. This includes the ductwork itself, the exhaust fans, the supply air, because if you are exhausting air, you need to make sure that you are supplying enough air so that the blower is able to do its job and is not starved of air, and as well as the installation. So there is a lot that goes into the ducted fume hoods that really need to be thought of on the front end of the design phase, and can cause some additional costs in the build. So that was ducted fume hoods, and the other form of fume hoods that we're going to talk about are the ductless fume hoods, and these come in three types. You have the DH1, the DH2, and the DH3 setups. So ductless enclosures, as they sound, have no duct, which is a great benefit. And how they are able to do this is through carbon filtration. So these filters, they capture the chemicals that are being brought through them and are able to recirculate clean air into the lab space. Most of the time, your application will need to be reviewed by the manufacturer or someone involved in that to make sure that it is applicable to what you're doing in the lab, because not every application is suited for this. It's not a substitute for every hood. There are a lot of benefits that come with a ductless enclosure or ductless fume hood, and one of them would be energy efficient. As I've stated before, the ducted fume hoods will take air out of a building that has been tempered to the comfort level of the lab and is exhausting it out of the air or out of the lab space. Then air has to be supplied into the lab, so untempered air has to be brought into the lab space. All of this takes money, and to make sure that the lab space, the air, the temperature, the humidity, all of it remains constant. With these ducted hoods, no air is exhausted. So that is benefit in that it doesn't have as big of a burden, or doesn't present as a bigger burden on an HVAC system. The next benefit is that they are environmentally friendly. So ducted hoods will take these chemicals and hazardous vapors and fumes, and they'll exhaust them into the atmosphere. With the ductless enclosure, you're capturing those, and then you're taking these filters that have been loaded with these hazardous materials, and then you're disposing of them in an environmentally friendly way. The next benefit is that they are very flexible. They offer flexible installation. They are able to be put in the bottom building or the bottom room of a very tall building where ductwork does not seem plausible. They're able to be put in a building that is very old, and adding new infrastructure to the building would seem very expensive and very labor intensive. So this added dimension of flexibility is a very big benefit of these ducted fume hoods or ductless fume hoods. As I've mentioned before, there are different types of ductless hoods, and that's in their DH. This is defined by CIFA 9. And we're going to talk about the different DHs, the DH1, the DH2, and the DH3 next. First, we're going to start with the DH1. The DH1 it has a filter, it has a carbon filter, but it's mainly for non-toxic or nuisance odors. These also do not have a chemical sensor. So pretty much with a DH1, a ductless hood 1, anything that you could do on an open bench, you can do in this hood. Things like cover slipping or staining. So it's a very simple application that these are designed for. Next, we have the DH2 hood, or ductless hood 2. This hood meets all of the DH1 requirements, plus it has different types of filters, like inorganic filters or ammonia filters or different kinds of filters that you can order based on what your application requires. They can also handle manufacturer-approved toxic chemicals, often determined through a chemical assessment form. Another thing about the DH2 is that they do have a chemical sensor to detect breakthrough, unlike the DH1. These are not typical fume hoods, though, as you can kind of see. The sash here, the opening, just lifts up instead of rising vertically and seamlessly. There's also no room for service fixtures, such as air, gas, electrical, or anything that you might need for the fume hood. Finally, we will talk about the DH3, or the ductless hood 3. Now, this hood meets all of the DH2 requirements, plus, and this is a big one, it has a secondary backup filter. And in particular, the secondary filter is identical to the primary filter. Where the DH2 lacks in safety is that if you are using the hood and the chemical breakthrough sensor goes off, well, you don't have a whole lot of time to clear out everything that's in the hood. Once that chemical sensor is going off, there's a potential that that chemical or that vapor is escaping into the lab space. With the DH3, it has a secondary filter. So even if that alarm goes off, you still have your secondary backup filter that will protect you for as long as it takes to decontaminate the hood or just get everything out, and then ultimately replace the filters. These filters are of one kind, and they're built to handle acids, solvents, and bases. So again, the difference here between the DH3 and the DH2 is that the DH3 just offers a new dimension of versatility in that you don't need to buy multiple types of filters. You're good with the one, which is a big benefit. These hoods are also the closest thing to a ducted general chemistry hood, without being ducted to outside, of course. These, as you can see in the picture, it is a full-size hood. The sash raises vertically instead of hinges, and there's also slots on the corner posts that allow for the installation of service fixtures such as the air, gas, and electrical. So now I wanted to go over a cost analysis of different types of fume hood configurations that will allow you to decide what is best for my lab. The first one I want to talk about is a conventional fume hood or a constant air volume situation. This is a scenario where the quantity of the exhaust air never changes, hence the name constant air volume. No matter where the sash is or the components inside the hood, you're always exhausting the same amount of air. And for this situation, or for this analysis, we're going to use a specific exhaust volume of about 1,200 CFM. This is pretty typical for a conventional 6-foot benchtop fume hood. The initial costs on this would include the fume hood itself, as well as the building infrastructure, the mechanical, electrical, and plumbing. And we're going to take a look at this in a table format. You can see here the benchtop hood itself is about $14,500. The building infrastructure adds on another $20,000, and then which means the total capital equipment cost is about $34,500. Out of all of the systems that we're going to look at, this is actually the lowest initial cost of the three. But you'll notice where it has a low initial cost, it makes up for in the operating and maintenance costs. Specifically, the makeup air column of having $9,600. It's a pretty large number and equates to about $12,167 a year of operating and maintenance costs for that one hood. It's a pretty significant cost, especially when you see what the next couple of hoods will bring. The next analysis that we're going to do is on a variable air volume fume hood. As the name suggests, the VAV means that the quantity of the exhaust air actually changes to maintain a specific face velocity. So in the CAV, what remains constant is the air exhausted, and at VAV, what remains constant is the face velocity. And in this situation, a typical 6-foot benchtop fume hood will be able to operate on about 800 CFM average. The initial cost for this type of fume hood includes the fume hood itself, very similar to the CAV, as well as the building infrastructure. And finally, it requires VAV integration with a whole nother system. This does add a little bit more of initial cost, as you'll see in this table. We can see a comparison here between the constant volume and the variable air volume fume hood, in that it does have a larger initial cost at the $39,500, about $5,000 more. Where it makes up for that is going to be in the operating and maintenance cost. And again, drawing attention to the makeup air portion of this table, it only requires about $6,400. And this number comes from taking about a typical cost for a fume hoods as per CFM is about $8 per CFM per year. And that's where we're getting these makeup air numbers. And the VAV overall has about a operating and maintenance cost per year of $8,811. So there are significant yearly cost savings by going to a variable air volume system. And last, we're going to look at the Echo filtered fume hood. This is a ductless fume hood that we've sort of discussed. And in these hoods, air is filtered and then it's recirculated into the room. This means that the exhaust volume is 0 CFM, much less. The initial costs are very similar in that you do need the fume hood, but where these hoods differ is that you need to order the filters that go with the fume hood. They are a separate cost. I wanted to look at a final cost analysis with all three of these put in one slide. You can see that the total cost, total capital equipment cost for the Echo filtered fume hood is actually less than that of the variable air volume fume hood at $38,520 approximately. Where this hood really excels is in that makeup air portion. It has $0 per year since you are recirculating air. In that $8 per CFM does not apply here. It does have a little bit higher of maintenance costs per year because you do have the filters associated with the fume hood, but that $2,093 of total operating and maintenance costs per year more than makes up for that. So those are the types of fume hoods and ways that you can explore to see what kind of ways you can increase your lab's efficiency. But I wanted to pass this on to Ken Crooks with Erlab to explain how these filtered fume hoods are able to do what they do and perform the way that they are.
All right. Thank you very much, Kasey. Good job. Appreciate that. So, and thank you all to our viewers for your time today. Appreciate that too. So we look at the filtration and we want to know, how does it work? Obviously, it's very important. It's pretty simple how a ducted fume hood works, but how does a ductless hood, especially a DH3, the best of the best here? So I just want to work logically. This is a module or stack of filtration technology sitting on top of the filtered fume hood. And starting at the bottom, you first off have a light. The hood users need to see what they're doing, of course. And then above that light will be some pre-filters. There are optional different pre-filters. We'll talk about that in a couple slides. And then on top of that base module would be a HEPA filter if you're working with hazardous powders. This is not required, this is optional. And if you're not working with any hazardous particulates or solids that may become particulates or high temperature acid use, then you would not need the HEPA filter. And I'll talk about how we determine when and where. On top of that would be the first carbon filter. So this is the one I like to describe as doing all the heavy lifting. This is doing the chemical adsorption day in and day out, capturing everything generated within that hood and stopping it at that point. Coming off the outlet side of this filter will be very clean air. And I'll talk about just how clean in a minute, amazingly clean. On top of that now would be the fan box. And so just like Kasey was describing with the remote blower configuration or the manifolded VAV system that has the hood up on the roof also, this fan, has the fan up on the roof also. This fan is drawing air in through the open sash, up through the cavity of the fume hood, capturing whatever is being evaporated and vapors and whatnot used inside that hood, and then drawing it up through the filtration column. So again, any leakage would be clean air into dirty, not contaminated air blowing out. I mean, this is a very important point, and of course we comply with that also. And then lastly, sitting on the very top of this is that safety filter. So after the fan and the detection area, that's also where the sensors are located, we place a redundant, fully redundant safety filter on top. So once we detect molecular breakthrough of the primary filter, and we sound that alarm down to the user, we also have that secondary safety filter sitting on top to capture whatever molecules did break through and still return clean air back into that laboratory. Very important differentiation with the DH3 technology. So how does it all look? This is a 6-foot wide fume hood. You can see, if you count, there's 4 modules of filtration stacked up in there. And so this is our latest generation of technology, and we're very excited to release this with Labconco. And our goals were to improve the filtration capacity for solvents. Solvents, and I have a slide coming up on that, solvents are the most challenging chemical you can use. They're also the most common, but we've got that figured out, not to worry. Secondly, ease of integration and installation. And so this lower image here where the 3 base modules are in descending order there, they basically are, I have kids, you'll realize when I say this, they're like Legos. They interlock and they stack and they distribute power and communications both horizontally and vertically and self-configure. So that was a huge step in the right direction for ease of integration and installation for our dealers and making sure that you, the customer, are handed over a fully working filtered fume hood. Next up, we wanted to improve the detection by adding more sensors. So there's now an optional formaldehyde sensor, especially with the new safety limits on formaldehyde exposure. It was very important to get a specific sensor for that for the applications that are using formaldehyde. You don't need it if you're not. Also a relative humidity sensor in each fan module. And the temperature sensor was already there, but we've now moved it up into each fan module also. And then lastly, adding an anemometer. So we'll measure directly the face velocity. And so that's the speed of which that air is moving into the fume hood. It's a very good indicator of safety, though containment testing is the final indicator of that. We wanted to expand the communications so you can still hardwire to your building network. My kids, back to them again, my kids look at me cross-eyed when I say hardwired. No, come on now. So we have Wi-Fi and Bluetooth capabilities also, so much easier connectivity there. And then the configuration and flexibility. There are different pre-filters you can use along with different sensors you can use depending on your specific application. But as Kasey had also mentioned earlier, there's that one filter type that handles acids, bases, and solvents simultaneously in much higher volumes than in the past. And simplified the maintenance also, of course. With these improvements now, it's much easier to maintain these hoods. It was pretty easy before, but it's a lot easier even now. So I mentioned solvents, that first goal. We don't have to go through all these details. I don't want to bore you with these, but again, solvents, because of their volatile nature, have always been the largest challenge with chemical molecular filtration, activated carbon type filters. And so we've done a few patented things here that have really expanded our capacity. The example graph here is ethanol. We've increased it over 600% the time before some level of emission is sensed after the filter. And the first column on the graph on the left, middle column, the 1% of TLV, threshold limit value. So that is a value of exposure that's allowed by the American Council of Governmental Industrial Hygienists. And TLV is not a short-term exposure, it is a lifetime exposure. So 8 hours a day, 5 days a work week, 40 years of your life. We're guaranteeing to you detection and alarming at no greater than 1% of that already very low limit. And so how that plays in here to our capacity, these are capacity increases before we sense greater than 1% on the outlet side of the primary filter. So just a real dramatic increase. Is there still room for improvement? Heck yeah. If you're going to use diethyl ether or cyclohexane, those are challenging, and we'll want to use those with really a focus on limiting evaporation. So very, very small amounts, and keep it capped and covered when you're not using it because it's got a low boiling point and it wants to evolve very quickly. I think you know that if you use them. So sensors and detection, how is it we go about that 1% TLV exposure that I just talked about? So first off, there's an acid sensor in there, a whole suite of sensors, and a solvent sensor that are both located up in the fan modules. So when that primary filter is no longer at the efficiency that we all want it to be at, we will detect that and we will alarm. Meanwhile, coming back into that laboratory is clean air, no greater than 1% of what you're allowed to be exposed to. So it could be 99% and you'd still be safe. Our guarantee to you is less than 1% of that, just to be extra safe. Additionally, we have that optional formaldehyde sensor. We expect that to be in about 15% of the applications. Not too commonly used, but when it is, it is. And then that temperature and humidity sensor also. And lastly, that anemometer sensor. All of these add up to safety. If we're sensing it, we're detecting it, that's going to bring to you safety as a hood user. But we need to know how you're going to use these hoods. As Kasey talked, I think, very early on, this isn't for everybody. Ductless hoods need to be approved each and every time for your specific application. So any reputable manufacturer will come to you with a chemical questionnaire, and this is a lot more than just a chemical list. A chemical list is a good sort of go, no-go gauge place to start, but we need to better understand not only which chemicals you're using, but how you're using them. What is the type of handling? In this case, we have a couple of recrystallizations, some evaporation, thin layer chromatography, so forth and so on. Then you tell us the chemical, you tell us what type of container it's going to be housed in. That lets us know how much evaporation may happen when it's open. You tell us, is it primarily open or closed? What's the dilution or concentration? The temperature, vitally important to know the temperature you're handling that chemical at. How often do you do that handling? On average per month across a year. And then each time that you handle it, how many milliliters or grams, depending if it's a liquid or solid, and then for how long. And so armed with this level of information and detail, which is a little bit of work for your hood users to complete, but once it's done, it's done. We can go through there and be absolutely sure that your application is either approved or denied. And we typically deny about 25 to 30% of the applications each year. And if we don't approve it, we won't let it be sold. It's really just that simple. Safety first. And in that report and that approval, we'll go through everything provided by the hood users, and we'll, from a safety perspective, at the very top of this slide, we'll look at containment. Is everything you declared to be used in this hood going to be contained by the hood? Now, this doesn't matter if it's ducted or ductless. At this case, we're just looking at what is it you're using. And an important part of this also is just making sure that everybody knows, to be crystal clear, this is a chemical fume hood. This is not a biosafety cabinet. Sometimes we say filtered, people start to think of BSC, a biosafety cabinet, which is also HEPA filtered for biologicals. Biologicals are not approved for use in these hoods. So we'll double check that on the chemical list. Detection, is everything declared is going to break through those filters? Will we be able to detect it? Will the filter then be compatible with everything on that list? Will we capture and contain everything on that list? And then lastly, life expectancy, which approval of that is really more up to the end users. So on that point, in the middle here under the filtration section, is filter life. Now a little internal speak, sorry for this, the M1 through M6, that's the hood size, going from a 3-footer up to an 8-footer. So for an example, an M4, 4 modules of filtration, that is a 6-foot wide hood, very common application in undergraduate chemistry teaching labs, for instance, our most prevalent application. And in that case, we're guaranteeing for this customer 48 months filter life, very typical for what we see, again, especially in teaching applications. If the HEPA filters are required, we'll check that off. If the acid and ammonia pre-filter options are required, we'll check those off individually or as shown here together. It really depends on which chemicals you're using and how we can maximize the overall Nutridyne filter life and your safety. So that's where the different pre-filters, that configurability we talked about earlier, comes into play. And then lastly, based on your specific application, we will fine-tune the sensitivity of the breakthrough detectors, the solvent sensors and the acid sensors, just making those appropriate for the hazards or lack of hazard of the chemicals you're using in that hood. When we look at how we know all this, I mean, how is it that one company can know all this information? We've been doing it for over 50 years. We have our R&D lab over in France. This is just a quick picture of it. Not to brag, I just want to say this is the level to which we go. We've got filtered storage cabinets, ductless hoods, the filtration technology that Labconco uses on their filtered fume hoods, ceiling-mounted fan filter units. We know filtration. It's what we do. And then in the middle of that back there is a little bubble, our test chamber. I'll talk about that in a moment. So when I talk about the go, no-go, the chemical list, we have 2 different lists. The short list is the no-go list, if you will. And so these are chemicals that are not retained well by any type of carbon filtration. And the best way to look at that is they have low boiling points and low molecular weights. Therefore, they're gaseous at standard temperature and pressure. And this list is basically what you would expect. Hydrogen, all the noble gases, methane, ethane, carbon monoxide, carbon dioxide, nitrogen monoxide, you can read SOx, NOx. And so these are the most common gaseous chemicals. Now the good news is they're not commonly used in laboratories. And some of these aren't even hazardous, not in the concentration that would be released into the laboratory, but some of them most certainly are. So if you're using any of these, and you're using them in higher volumes, it's probably a no-go for a filtered fume hood. If you're using them in lower volumes, and I know higher and lower, that's always a difficult subject. What is high, what is low, what is a lot, what is a little, what is medium? Really depends on the frequency and the quantity used. I like to think of if it's less than 200 milliliters a couple times a month, I think we've got something, I think we've got a solution for you. However, the real point here is your environmental health and safety officer definitely needs to be involved because we're going to look at what will happen if those chemicals, and again, it's only these chemicals, would be released into the lab. How quickly would they be diluted and removed from that lab through the ventilation? Again, the good news is not commonly used at all from our experience, which is great. Now, it's not just the chemicals, it's also which applications are not recommended for a filtered fume hood. I mean, this is the no-go list, right? So if you're a chloric acid hood, if you're a radioisotope hood or acid digestion type hood, definitely stick with your ducted hood. That's a special build, a special part anyhow. It is not a candidate for filtration. Highly exothermic reactions. One thing to remember about filtered ductless hoods is they do not remove heat from the laboratory. So unlike a ducted hood, which would, it would exhaust that heat right outside. Filtered hoods would not. They would return that heat right to the lab itself. Again, really not a problem for your teaching classes. You're usually working with smaller amounts. You can absolutely use Bunsen burners in these hoods and heat your samples and whatnot. That's not a problem. It's just that if it's a really exothermic type reaction, especially if it generates a lot of smoke also with that, carbon filters do not capture smoke. The optional HEPA filters will capture most smoke particles. I think there would still be a slight smoke odor that would make it into the lab though. So these are, again, things to consider on the no-go list. Mercury, not commonly used anymore, thankfully. We can capture it really well. Problem is we can't detect it, so we put that on the no-go list, not down at the TLV level required anyhow. And then anything that's high toxicity or basically immediately lethal, those would not be used in a filtered fume hood. All right, so then how do we know that? Again, getting down to the nitty-gritty here. So we have our test bubble here in the back of our laboratory in France, and we have our GCMS machine, and we have gone through hundreds of chemicals, the most commonly used chemicals in laboratories today, and those 700 plus chemicals represent thousands of chemicals that will respond in a very similar manner to molecular adsorption, activated carbon molecular adsorption. And each one of those is tested at least 6 or more different concentrations, and then each one of those individual tests is performed twice, a minimum twice, just to make sure of repeatability. So we're absolutely confident in our capacity charts, and we know exactly how much we're going to capture before you're going to have greater than 1% TLV breakthrough on that filter. And then again, they represent thousands of different chemicals, not every chemical, and so if you've got a chemical that's not on our long list, we absolutely can review that and even test that in this chamber in our laboratory. So that's the test bubble, that's the GCMS, which is no great deal, everybody knows that. It's just a very large investment for us in testing instruments, but very much required. And so with that, and with all that testing, for now decades of testing, we have published our latest edition of the long list. This is the chemical list that is now over 60 pages long of the chemicals that we know exactly how much we can adsorb, and from that we'll know how long the filter will last in your specific application. Maintenance. Kasey talked about how, in his slide, about $1,800 per year is the average operating cost, and that is replacing the filters, maintaining the system, make sure it's working year after year. So it's not makeup error, that's the great thing, because that's much more expensive. And so when it comes time to replace the filter, it's a very easy system. We call it a revolving system. I wish it were a crank handle and it would revolve on its own. It's not quite that simple. You do have to lift off the old filter and put the new one on, but not a big deal. It's 25 pounds at the top of a 6-foot ladder at arm's length, easy to do. And so the first thing you want to do, obviously, is wear your standard PPE, gloves, glasses, if required in your lab, a lab coat too, absolutely not a problem there. You do not need to wear a respirator. That is not required. Once the chemical is adsorbed by the carbon bed, it is staying in there. The molecules are not coming out. You could lift the filter off, accidentally drop it on the floor from, again, the top of that 6-foot ladder, and it won't, but if you manage to break it open, we have it compartmentalized so it wouldn't do that, but if you manage to break it open somehow, you'd have carbon granules on the floor. It'd be quite a mess to sweep up, no big deal. I've never done it in 7 years, but again, could be done. What you wouldn't have, most importantly, is you wouldn't have liquid chemicals, you wouldn't have escape of molecules. They're all in that carbon structure, held there, not to be released, not under normal atmospheric conditions anyhow. So you would then take the secondary filter, the one that's on top, that safety filter, move it down to the primary position, so it can start doing all the heavy lifting, as I call it. Step 2, you would put a new secondary filter on top. And then step 3, you would package the old primary filter in the heavy poly bag and cardboard box that the new filter came in and send that off for environmental disposal. And there's a couple things there. Easiest and simplest, most direct is out for high temp incineration as hazardous waste. The good news is carbon filters have a lot of embedded energy. Coconut shells, activated coconut shells is what we use as our medium, and the best on earth, 15,000 square feet of surface area per gram. All of that is adsorbed chemicals. Now you have a lot of embedded energy that the incinerator will put back up on the electric grid to the tune of around 78 kilowatts per filter. I mean, tremendous energy back up on the grid from each one of these filters. And what comes out of that, per EPA requirements, you must have a 99.99% efficient incinerator, is basically one molecule on a 10,000 gets out into the atmosphere up the stack. There'll be some CO2, there'll be some water molecules, but 1 in 10,000 molecules of the chemical make it up versus 10,000 of every 10,000 on the ducted hood that you didn't use when you chose the filtered hood. There is an option to do the T-clip or TCLP and testing to make sure nothing leaches from these filters, and then the filters can go out as standard household waste. That testing is expensive though, so you'd have to have a lot of filters at the same time, and that's worked for some of our customers. Just throwing that out there as an option. And then obviously, because now the fan has also been removed and put back in place, the filters have been changed and rotated, you need to recertify that hood. Filtered hoods, just like ducted hoods, just like ductless hoods, should be annually recertified. And that's through a third-party independent company with no stake in the game whatsoever. They come in, they read phase velocity, they make sure you are running a safe hood at that sash operating height that you've previously dictated. When you look at the absolute best benefit of using filtered fume hoods, it is the 20-year operational carbon footprint. There is a 94% reduction, and many thanks to BR+A consulting engineers in Boston for doing the research here, looking at everything from transporting the carbon to making the filters to incinerating everything after the fact to the metal work that goes into a ducted hood versus a filtered hood, same metal cabinets, same Labconco structure, but avoiding, as you can see in orange and red, avoiding most of that electricity cost and all of the gas cost if you're in a zone that needs to reheat, you will see a very large reduction in the carbon footprint. So when it's safe to use for your application, which each application must be blessed ahead of time, there is a tremendous environmental and monetary benefit to using the filtered fume hood. All right, Kasey, I think it is back to you now.
Thanks, Ken. Appreciate you providing that information. So by now, you've learned what a ductless fume hood is. You've learned about the benefits that it can have on an HVAC system and improving the efficiency of your facility. And you've also learned about how it works and how it's safe. But now let's talk about what Labconco has to offer in these types of products. First, we have our Echo, which is a full-size fume hood. As I have mentioned before, it comes in multiple widths. It comes in configurations that has no windows. It has side windows, which is what is shown here. And it also has side and back windows that allows for a 360-degree view of a hood interior, which is great for teaching applications. We also have a smaller, more compact version of the Echo in our Aero. It has a shallower depth and also comes in shallower widths. It's also a little bit shorter, so it provides a good option for situations where maybe you have a smaller footprint in your lab space, or you have reduced height in your ceiling, but still need a ductless fume hood to operate your applications inside of. There's also an Echo floor-mounted fume hood, which is very unique. It's a one-of-a-kind fume hood, and it is completely ductless, and it comes in multiple widths, the same widths as the Echo benchtop, but also comes in 2 additional depths because these hoods are made to be, they're made to house large pieces of equipment. So there are a lot of different sizes in shapes to meet your application needs. So that's what Labconco has to offer. But I want to talk about the process of going about getting a ductless fume hood. The first step that needs to be done is an LPQ, or chemical assessment, needs to be filled out. As I have mentioned and as Ken has mentioned, this is a very important step because it determines the filtration compatibility and the requirements. There are certain things that we can add to the filtration column that can maybe handle a certain part of your application, and ultimately make sure that the longevity of these filters and the safety of the operator are ensured. And next, you need to identify the appropriate hood. As I mentioned in the previous slide, Labconco has a variety of sizes of fume hoods. So in identifying this, you'll need to take into account the size of equipment that you may be using, or the available space that you have in your facility, and ensure that you are selecting the proper fume hood for your application. Next, most benchtop fume hoods, or all benchtop fume hoods, need somewhere to sit, and that's where a work surface would come in place. Something to take into account would be the size and a sink location if you're using water and need to dispose of it. That would be something that you should take into account. And then finally, to specify any service fixture requirements that you have, whether that's water, air, gas, electrical, vacuum, pretty much anything that you need to put in your hood, you need to make sure that you're having that accounted for. So that's what we have for the filtered fume hoods in improving your lab's green initiative. I appreciate you taking the time to listen to this presentation, and I hope you can take something away from this, and I look forward to answering any and all of your questions. Thank you.
Thank you so much, Kasey and Ken, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Our first question, what is the average lifespan for a set of filters?
So the average lifespan, it definitely depends on the application, but we found that it ranges from about 2 to 5 years, 5 being the max and 2 typically being the minimum. So it's in that range is where they will typically fall in longevity.
Wonderful. And the next question I have, what kind of spaces can filtered hoods be utilized?
In pretty much any space, there's oftentimes a good mix of ducted and ductless fume hoods for an individual lab space, but where these ones are more versatile or like modular labs or temporary spaces, if say you're moving into a new lab and you have like a lab space outside that's in a trailer or something that you still need to perform your applications and your procedures in, they're great for that as well, since they can be moved into the permanent lab space after it's finished.
Yeah, I agree, and I'll just jump in there if you don't mind. The swing space is quite a need right now with renovations and new construction and education facilities. And that's been a really good application for these hoods also for exactly all the reasons Kasey just said. So definitely think of them for that. And if you've got an application that is understood, repeatable, a certain level of administrative controls also help. This is an engineered solution, but you do need administrative controls when it comes to a filtered hood. That's, again, why I think the education marketplace, higher ed, is our #1 application.
Thank you so much for that. Okay, the next one I have coming in. Does the DH3 have baffles in the back? And if not, how are we dealing with the issue of airflow around objects on the work surface?
That's a great question, and one that needs to be asked. So no, they do not have baffles in them, and that's actually by design. So what does a baffle do? Is it draws the air back away from the sash and then up. Well, that would actually load the filters in the back and risk the sensors going off before they're able to. And Ken can confirm that for me if he can. But
Yep.
To expand on this is that these hoods, even without the baffle, have been put through a modified ASHRAE test. In that modified ASHRAE test, they use the isopropyl alcohol and they still have very low detection limits, which is showing that the hoods are still containing even without the baffles.
Yeah, I'll jump in. Thanks, Kasey. Exactly right. And so that's the modified. So testing in the field, because SF6 or NOx, the typical tracer gas, is now in place, even though ASHRAE is changing that. The SF6 NOx, they will go through the filter and invalidate the test results. So we've got that modified test procedure for in the field. At the factory, the fume hood manufacturers do a full and complete 110 test. You know, they attach a duct to the top of it where the filters are and exhaust that tracer gas so that it doesn't invalidate the results. And correct, we pass amazingly well without the baffles in the back. The thing to remember here is instead of trying to cram all that air through a 10-inch duct collar somewhat centered in the top of the hood, the almost entire surface of the ceiling of the fume hood is the exhaust port. Those multiple stacks, I showed an example of a 6-footer with 4 filtration columns. Those multiple stacks or columns or modules of filtration draw the air up, certainly not laminar flow, not technically anyways, the Reynolds number is not 2000, but in a nearly linear fashion, and we get a much better flow coming in and up and through and out. So much more reliable, actually, than trying to put it all through a 10-inch duct collar, which can be done, and you guys have solved that problem too. Good question. Thank you.
Wonderful. Thanks so much for your informative answers, and thank you to the audience for asking these great questions. The next one I have is, what climate is your makeup air cost calculated in?
So that's also a good question, because that number will fluctuate based on where the hoods are installed. What we have found is that so that calculation is done on about $8 per CFM, and what we have found, the range is about $5 to about $13 per CFM, depending on where you're at. So it is an estimate number, but it's kind of in the middle of what we've seen to kind of give as accurate as a number as we could.
Wonderful. The next one, are the new generation filters compatible with the previous units?
Sure, I'll jump on that one there. So unfortunately, the answer to that is no. To embrace a lot of the new technology and the new approach, we really had to sort of cut the umbilical cord, if you will. So there is no backwards compatibility to the existing filtered fume hoods. We'll still make the filters to obviously support those customers for the life of those hoods out there. There's thousands of them at this point. But we needed to really take a giant technological leap forward, and that required that we could not hold backwards compatibility. We love to, and that's always a goal on all of our new products. However, we just couldn't do that in this case. Thank you. Very good question.
Wonderful. Thank you again, Kasey and Ken, for your time today and your important research. We would also like to thank Labroots and our sponsor, Labconco, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of your registration. This webcast can be viewed on demand. Labroots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until then, stay healthy and safe. Until next time, goodbye.